now that we have our model built, we can plot the model fit. Right? So we've got the presence absence as a function of depth with the Nelson data. Let's make the plot look a little nicer. Specify different parameters for it. So we've got our plot there. Right? In order to then predict, or rather to plot the model fit, we need to use the predict function as we did before. Right? AB line is not going to cut it like it does with simple model fits for LM objects. We really need more than that. And so the predict function, as you'll recall, requires a new data argument. And so let's make a new depths set of values here. Make it a data frame of depth. Make this depth vector a sequence. Again, I like to extend this beyond the range of values that we've got, so the model kind of does continue off the sides of the plot, and specify length out of 100. So we want 100 values in between -5 and 15. That sequence then is assigned to this depth column in our data frame, new depths. So we've got that. Now, let's predict the values of presence absence. So we make a new object and use the predict function here. Feed it our GLM object, feed it the new depths, so new data equals new depths, and then the type is going to be link, and we want the SE fit to be true. And so when you write out the predict function like this, what we're saying is take the new depths, take that sequence of new depths, those 100 data points between -5 and 15, and for each one of those, predict the value of PA using our model, and return those predictions on the link scale. So they're going to be logit transformed values. And again, the reason we're saying this and not response, right? If we said response, it would kick it back to us on the real world scale, on the scale of our response variable, which is a value between 0 and 1. But we're trying to calculate confidence intervals too. And if we do that and then calculate our confidence intervals are very likely, almost definitely in this case, going to extend beyond 1 and 0. And those confidence intervals are then going to include unrealistic values. And so then we're kind of violating assumption 1 again. We're predicting unrealistic values, and our model's not as useful as it could be. And so what we need to do is say type equals link. Predict these values on the link scale, on a logit scale. And we want the standard error estimates for these. So when we run that, this PA pred object now contains, importantly, a list of the fit values, 100 values of the model fit, and then the associated standard errors. And so with these values, then what we can do is create a new type 3 mod fit. We'll make a new data frame. And use this then to plot what we're trying to plot. Let's have our fit is going to be, so I'll start with this way, PA pred fit, right? That's our fit. Remember, it's on the link scale. And so since this is on the link scale, what we need to do is take the inverse link function of it. This is how we would do that. We can use that plogis function, because as you'll remember, that's the inverse logit, plogis. And so when you wrap plogis around the PA pred fit, it's going to return these values, whereas if we look at what the pred fit function contains on the link scale, the numbers range from, look, I'm seeing -9, and then I'm seeing +8. Right? So those numbers don't make any sense in the real world. You can't have a probability of -9. That's absurd, because those are on that logit transformed scale. But when we take the plogis of those values and run just that, now you'll see that these make a lot more sense. We're basically ranging from very small numbers near 0 up to very large numbers near 1. So we're still bounded by 0 and 1 now. So this is why we take the inverse logit, the plogis of our fit there. But we don't only just want the fit, we want the upper 95% confidence interval. And then we also want the lower 95% confidence interval. And so the upper confidence interval is PA pred fit plus PA pred standard error fit times 1.96. Okay, drag that a little bit. And so this then, taking the standard error estimate times 1.96, that moves it 1.96 standard deviations from our model fit. 1.96 is the 95% confidence interval for the upper bound, at least. We add that to our fit value, and this whole thing is going to give us then the value of the upper confidence interval. But as I said, right, need the p-logis. Got to wrap all of that in the p-logis function. That's what's going to get this onto the real-world scale. And then we do the same thing. We just copy that over for the lower confidence interval, but instead of plus, make it a minus, because this is the lower confidence interval. We're subtracting that unit of PA pred times 1.96. We're subtracting that from our fit. And so with this, there we go. We've got this new data frame that contains 3 rows that are now back on the response scale, because we use that p-logis function around every value that we fed it, predicting the fit and the upper and lower confidence intervals. And you'll see that these upper confidence intervals don't go greater than 1, and the lower ones don't go below 0, which is exactly what we want. Now let's drag this back over. We've got our plot still up there. And so let's plot the fit of what we've just got here, type 3 mod fit object, and then from within that we want our model fit, and then we want new depths, $depth, color equals red. Let's do that. So if we plot this, there's our model fit, right? Beautiful, nice logistic curve here, which is what this kind of S-shaped curve is called, where we can see that the model fit does not extend beyond 1 or below 0. It is kind of capped. It's bounded in those directions. So very realistic model, much better than the model that we had before, where this black, straight Gaussian linear model just extended in both directions forever. Now we're bounded by 0 and 1, so much more realistic. Now we can also then plot the upper confidence interval. New depth. Let's also do it in red, but let's make the line type dashed. There's our upper. Now let me copy this over, and we'll do the lower. Boom. Inspecting this plot now, we've got our model fit, the solid red line, and the dashed red lines are our confidence intervals, the 95% confidence intervals. If we had not done that whole process of creating a new data frame with the p-logis function, these confidence intervals would have extended above 1 and below 1. But making the confidence intervals on the logit scale, on the link scale, and then transforming the confidence intervals back to the response scale is how we get it to look this nice, where these confidence intervals, just like the model fit, are bounded by 0 and 1. So we've got a very realistic model fit going on here. Beautiful representation of a binomial family generalized linear model.